Okay, we're at gotomath.com. Go down to differentials. No, that's not what we're doing. Yeah, that is what we're doing. Man, I just lose my mind all of a sudden. We're down here doing force, so let's click right there, bring that up. You can also click on the buttons. I added that feature. I thought that would be a whole lot faster. Anyway, we got the radius of a ball bearing is measured to be 1.6 centimeters. If the measurement is correct to within 0.01 centimeters, estimate the propagated error if the measurement is correct. Estimated the propagated error of the volume of the ball bearing. Also, we're going to be finding relative and percent error. Okay, so we're going to consider this ball bearing to be spherical. Alright, so we're going to be using that. And 1.6 centimeters. Let's see, there's 2.54 centimeters in an inch. So, okay, well, that's obviously less than an inch. But that's a fairly big ball bearing. Big ball bearing. Okay, so let's write down, what do we need to write down? The radius is 1.6 and delta x is going to be 0.01 centimeters. Alright, I guess we can remember that. 1.6. What was 1.6? I already forgot. Oh, we measured the ball bearing. I lose my mind. They measured the ball bearing. That'd be the radius of the ball bearing. Okay. So the radius is equal to 1.6. And we'll go ahead and put our centimeters in there. Okay. All right. And we got this possible error, we call it we call this the possible error. So we have negative 0.01 and this is our delta R here, less than or equal to 0.01. So this is the radius, the possible error on the radius. All right. Okay. So we're going to consider this to be a sphere. How's that? A sphere. So we need to know what's the formula for finding the volume of a sphere. Well, remember, volume is equal to 4/3 pi r cubed. 4/3 pi r cubed. Right? Where r is the radius of the sphere. Okay. Now we want to approximate the propagated error in the volume, and therefore we're going to be differentiating v to obtain dv over dr. So we want to go ahead and take the derivative of this guy right here. Okay, so we have dv is equal, or dv over dr, we're taking with respect to r here. So we take the 3, bring it out front, but then we're just left with 4 pi r squared, 4 pi r squared. So let's go ahead and just solve for dv. It's equal to 4 pi r squared times dr, right? Times dr. Okay. Now remember, we're going to be approximating the volume, right? We're approximating the volume. So this is kind of like dy is equal to the change in y, remember? Okay, so we're going to consider these two to be approximate. All right, so just like we did earlier. Okay, pretty simple. And then remember, this delta r is equal to dr. Is actually going to be equal to dr, just like delta x is equal to the differential of x. All right. Okay. So basically what we're going to end up having now is, since these are going to be approximately equal to each other, we'd have delta V, okay, delta V, which is approximately dV, and I'll put an approximation sign right here, 4 pi r squared dr. Since these two are approximately equal, we'll consider them to be approximately equal to each other. Right? So all we need to do now is just plug our stuff in. So we have 4 pi times r, and of course r is 1.6 squared, and our dr, right, which is actually this. Now I'm going to go ahead and write, remember this is plus or minus right here, plus or minus 0.01. Okay, we got to remember this is plus or minus. Okay, that's actually an approximation symbol right there. Okay, and so therefore we got we're going to need to now multiply all this stuff together. So approximately, right, and I went ahead and did that, and I end up with 0.321. I can't remember. We're supposed to be rounding to 5 decimal places, it says, if needed. So 0.3216. Actually, that's going to be 70. 1, 2, 3, 4, 5. Yeah, this is a 6, and then it says 99. So this ends up being that. Now remember that this is also plus or minus. Okay, this is plus or minus, and we can't forget our units. What are we calculating? Volume, right? So this would be centimeters cubed. Centimeters cubed. Okay, so this is actually going to be considered our propagated error. I guess I'll write that out over here. All right. Our propagated error. Okay. And you know, you could actually round that up to like 0.32 or something like that. But anyway, our propagated error. So calculating propagated error is actually pretty easy. I guess I did need to write that the delta r is actually equal to the change in r, but delta v is approximately dv. Okay, so that's our propagated error. Now to calculate our relative error, which is something that we need to do, and you know what, I'll just scroll on up the screen here. So we are calculating relative error, calculating the relative error. And the way the relative error actually goes, it's pretty easy. It's just dv over v. dv over v, which is actually equal to 4 pi r squared. So the dv is 4 pi r squared dr. And then this down here is just the volume, which is 4/3 pi r cubed. 4/3 pi r cubed, which actually all reduces down to 3 times dr over r. Okay, so that just simplifies down to all that stuff right there. Okay, pretty simple. Now we're going to do the substitute for dr and r. We're going to substitute for dr and r. So I'm going to put an approximation symbol now, and we do the substitution, right? We've already calculated what the dr is. Remember the dr, well, actually that was actually given to us, wasn't it? That was plus or minus 0.01. Okay, and then down here below is the radius, right? That was the radius, which was what was that again? 1.6. 1.6. The radius of the ball bearing is 1.6. Okay. So this is it when it comes to relative error. This is all you have to calculate when it comes to relative error. All right. And so we'll plug that into the calculator. We got 3 times, let's see, 0.01 divided by 1.6, and I'm getting, we'll write it here, is approximately 0.0187. We'll just go on out to everything it gives me there. 2, 3, 4, 5. Okay. All right. And of course, now remember, this is plus or minus. Plus or minus. Okay. And alright, so that's our relative error, how to calculate our relative error. And you're not going to believe about the percent error. Percent. How you do that? Well, that's just this, but we just multiply it by 100, so 1.875%. Okay, that's percent error. That's all you have to do on percent error. All right. So there it is. It's not too difficult. Pretty easy stuff, actually. And I don't know, maybe we should go to the web page and compare our answers here. So let's remember what propagated error is. 0.32170. 0.32170. Round to 5 decimal places if needed. I don't know. Let's see, propagated error. Of course it says, I wrote plus and minus, but it's the same thing. 0.3217. Okay, it doesn't put the 0 there for some reason, but who knows. Anyway, good enough there. We got relative error. I hope that was it. Was that it? Let's go back. Yeah, plus or minus 0.01875. 0.01875. Somebody truncated the 0 off there, but it doesn't matter. And then, of course, just multiply it by 10, and you get the percent error. Okay, so that's how you do that. It's not too bad. Alright, I'm sure at some point in time in the future I'll be adding more problems to this differentiation, this section here on differentials, but for now I've got to continue on and try to finish Cal 1 in about 10 days. Okay, so meet me back here at Go To Math, and I'll see you there. And keep calm. Head out to gotomath.com. Alright, bye.